Okay, let's get started. All right. We still got exams here if you never picked yours up. Okay. Alrighty, so I think I'm recording. Yep. Alright, so we're all the way down here now in week 11. Oh, and I still have to post the supplementary reading. Okay, I'll do that later. It's a chapter from this nice textbook, Types in Programming Languages. Okay. I almost wish, I was just discussing with Jacob, I almost wish I could use this book, for the actual textbook for the course. I like that book a lot. But anyway, so hopefully the quiz wasn't too bad last week. Right, Q3. And we have PA5 due this weekend, Saturday as always, right before midnight. And we'll have a help session this week again. The plan is Friday, Friday evening in ARC, just like before. But you should definitely try to get started before then. Now, if you manage to do PA4 successfully, then PA5 will probably be a little easier. Okay, but if you didn't quite finish PA4, then you probably still have a bit of work to do to kind of figure out what was going wrong. And you can contact the TA to get a solution file if you don't have a working parser or a working interpreter. Okay, but you should really try not to do that, because even if you do that, you're going to have to understand how it works in order to use it, to extend it to PA5. All right? And what is PA5? It's just we're taking the old language and adding functions to it. Okay, we're going to add essentially lambdas, right? Anonymous functions, and then function applications, so that you can call functions, you can actually use them. So that's pretty much the real change here is just essentially introduction and elimination of functions. Right? You can create functions and you can use them in the language, and that opens up a whole can of worms. So this language right here, it had no way of performing iteration. Okay, you couldn't do loops or recursion or anything, and so actually all programs in that language terminated. Okay, there's no such thing as an infinite loop in that language, but then in the new one where we have functions, there is such a thing as infinite loops, and so it really is a fundamentally more powerful programming language, right? This one is Turing complete and the other was not. Okay, so you can do all sorts of fun stuff in Scheme 1, and all you need is functions to do that. Okay. Then of course, later on we're gonna add the type system to Scheme 1, and there are some interesting subtleties there when it comes to that, termination and stuff. So that'll be fun, but we're not there yet. Right? We're still untyped. But now is when we are going to start talking about types and typing judgments, type systems, the idea of type safety. Okay, so probably like in the second half of lecture today, I'll start talking about types. All right, but I suppose I have a little bit more to say about interpreting, or kind of just the big picture of where we're going with this. Okay, so I don't have this planned out super well here, but we can go ahead. Okay, so on day one, I think day one of the course, we asked the question, what is a programming language? Right, that's a day one question here. And, what did we say it was? It's, a formal language that can be understood by a computer, okay, for describing computations. Okay, we had some definition like that. But so now I can give you a kind of more precise definition that, at least, if our goal is to come up with a really precise mathematical account of what a programming language is, okay, then there is a kind of a better answer for what a programming language is. And it has a couple parts. Okay, so I can go ahead and I'm going to draw something. There we go. So, what is a PL? what constitutes a programming language? And we've seen one part of this. I'll draw a big circle. And the first part really is just the syntax. Okay? So if your goal is to go and define a programming language, then the first thing you do is define the syntax. And we've done that. Okay? And the way that you define a syntax is by giving a grammar. Okay, so we've done that here. Here was our Scheme 0 core language. And we said, here's the syntax. Here's the concrete syntax. So these are all the valid syntactic forms and the ways that they can be combined to produce new forms in the language. Okay, you're essentially specifying, the possible shapes that programs can take on. Okay, so there's the syntax. Okay, and then the other half, very roughly speaking, is the semantics. Okay, once you've got the syntax, now you can say, what do programs mean? In a systematic way. So we want to be able to come up with a way of really specifying the semantics of a programming language. Okay, but actually you can divide this into two halves actually. So we can split semantics up into two camps. Okay, on one hand you have the static semantics. Okay, and this is basically the type system. Okay, very roughly speaking, you have the type system. It's kind of one half of the semantics of a language. Okay, and then you have the dynamic semantics, which is the runtime behavior. All right, so the dynamic semantics is what's implemented by the interpreter. Okay, so far for our language, for our Scheme 0 core, we've seen the syntax and we've seen the dynamic semantics. Because, we defined the grammar, we wrote a parser that recognizes our syntax, and then we wrote an interpreter that implements the dynamic semantics. It tells us how the programs run. But what we haven't done is the static semantics. We don't have a type system yet. And so, in a way, you could say that what we have is just a very trivial type system that doesn't really say anything, right? Where there's sort of like, just some universal type U, and all the programs just have type U no matter what. Okay, so it's a sort of degenerate, trivial case of static semantics that we have. And so when we add a type system, we'll be enriching our static semantics to actually, not be so trivial. All right? Okay. But then, I told you how you can specify the syntax. That's with the grammar, right? And one way to specify the dynamic semantics is just to give an interpreter. That's kind of what you're doing. You're saying, well, here's the interpreter that's pretty easy to read. It's easy to see what it's doing. And so you can kind of take that as a specification of the semantics. And so then maybe later on you want to write a compiler or some more complicated way of implementing the programming language. And then you can use that initial interpreter as like a reference implementation. That's the spec, okay? Because it's so clear and easy to understand. Okay, and so then you just need to make sure that your compiler agrees with the interpreter. That's one way to do it, but you can also, there's some more like mathematical ways of characterizing the dynamic semantics. And there are a few major kind of schools of doing this, okay? So we're only going to look at one of them, but I'll go ahead and mention the other major ones. Oops. And I think the book does this as well. Okay. So there are a few ways of doing this. So one is called denotational. Okay, so denotational semantics. And all this is when essentially you'll give a function, a denotation function, which you might write using like brackets like this, okay? Where the dot means that's where the argument goes. And you say, well, this is just like a function from the syntax, which for us would be x, to some kind of mathematical domain, like a set or something. So you have some way of interpreting the elements or the programs in your language as mathematical structures. Okay, and it's a very general idea, and so you might just interpret expressions as functions. Well, maybe you think that you could interpret an expression as a value, right? Every expression has a value. Okay, but that's not quite right, because in general, expressions can have free variables. Okay, and so like if I said, what's the denotation of the expression like plus x1? Okay, what's that? Well, this is if you're trying to use value here. Well, you don't have one, right? So really, if you recall, that evaluation, it doesn't happen in a vacuum. That there's also a variable environment. So one thing you could do here is so we can interpret our expressions in our language as functions from environments to values, right? Because in general, that's what an expression is. It's just some expression that could contain three variables. Okay, so the value that it takes is actually a function of the environment. Okay, so we could have rewritten our interpreter to have this type instead, where this is essentially what we did already, where our interpreter takes an x but an n and gives you a value. And this is just kind of a curried form of the interpreter, where it's expressed as in a denotational way. We're saying, well, okay, every function denotes, every expression in our language denotes something of this type, a function from environments to values. So you could do that, okay? And of course, there are much more fancy ways of setting up denotational semantics, okay? But we're not going to do that, all right? Okay, there's another one called axiomatic semantics. I'm just going to mention this, but not really going to look at it at all, but that's things like Hoare logic, okay, separation logic, just so that you see these words. And if you're interested, you can look them up. But what we're really going to be looking at is another approach called operational semantics. Where you really are going to specify how programs evaluate. Okay? So it's not this kind of, like in a way, the denotation of an expression as a function from an environment to value, it becomes this abstract entity, this function that kind of forgets about all the syntax and everything. And so you lose information about how it actually runs. It just becomes a function from inputs to outputs. But with operational semantics, this is actually kind of syntax aware. It says okay, if you've got a piece of syntax that looks like this, like plus x1, then how do you evaluate? What are the steps? What are the operational steps that you need to take to evaluate the expression? Okay, and informally, I would just say, well, you first evaluate x, and then you evaluate 1, and then you can add the values together, and that's your value, right? There's a sequence of steps that you have to do. Okay? And even within that, there are some subdivisions. Okay? There's small step, which is where you really break it down to tiny steps of execution. But the one we're looking at, the one that we're using is big step. Okay, sometimes called evaluation semantics. Okay, so this is what we're using, and I can show you the big step semantics for our language, and it's this document right here. If it'll load, maybe. Maybe I'll try again. Maybe I can download it. Here we go. Okay, so it's the evaluation semantics, and here's just some fancy math speak. Okay, the idea is it's this relation that tells you how to evaluate expressions in our language to values. Okay, and let's take a look. Like the val rule, it just says under an environment rho, a value b evaluates to itself. Okay, that's how you read this. It's under this environment, this expression evaluates to this value. So we call it big step because it's sort of all in one step. That's why there's this downward arrow. It's saying, well, this expression on the left evaluates all the way. So we're not necessarily specifying like tiny little concrete details of how it happens. Okay? Kind of goes to a value all in one big step. Okay? There's the variable case where you say, well, under rho, a variable x evaluates to a value b if rho of x is equal to b. Right? So, you know, if rho contains a binding for variable x, mapping it to value b, then that's what x evaluates to. Okay? And then we have these other cases, like there's only one unary operator, not e. So we say, well, you know, under environment rho, the expression not e will evaluate to not b, where b is a Boolean, if e evaluates to b. Okay? So this is just a way of specifying the operational semantics of our language. This is how they run. This is their runtime behavior. Okay? Same thing for binary operators. You've got a binary operator that looks like this. Then it steps to value v as long as these things can be satisfied. Right? So if E1 under rho, the same environment, evaluates to some number n1, E2 evaluates to n2, and you know, b is one of these operators, and when it's applied to n1 and n2, you get v. Then that will be the result. That will be the value that the whole expression evaluates to. Okay, so you know we've got these for everything. I guess I can kind of run through. What about a let expression? This one's a little more interesting because we say, okay, well, suppose that E1 evaluates to V1 under the same environment. Okay, but then E2 should evaluate to some V2 under a modified environment. Okay, where you've just taken rho and updated it to include a new binding for x. You say, well, send x to V1, where V1 was the value you got from E1. Okay, so just evaluate the body of the let under that updated environment to get your final value. Okay, and then the conditionals are pretty straightforward. There's actually two cases for them, right? One for when the condition expression evaluates true. So then you evaluate E1 and that's your value. Or if the condition expression evaluates to false, then you evaluate E2 and that gives you your value. Okay, so you might ask like, well, what if econ here evaluates to a number or something? Okay, what that means is that neither of these rules applies. And so that means like you've got an error. Okay, so if at any point none of the rules apply, then well you can't proceed. Okay, so that's a runtime error. You know, it means you've gotten stuck. That's what you can call it. So a program can get stuck. All right. So that's our thing. And let's see, that was for Scheme 0 core. And there's another one, okay, for Scheme 1 core. Oh, whoops, did I add the wrong file? Okay, I added the tech instead of the PDF, so, okay. Oops. I'll have to fix that. But there's another one for you know, our next language where we have functions. And so if you're getting around to implementing the interpreter in PA5 and you wonder, well, how should it interpret functions or function application? Well, you can look at the evaluation semantics that I've given you, and that's your answer. Okay? I have to remember to fix that. Okay? Right. So, you should be aware of just be aware of what these are, okay? Just the idea. Not so much axiomatic semantics, because I didn't really say anything, but you should understand the idea at a high level of denotational semantics and operational big step at least. Okay? Because that's what we're using. All right. Right. So now that we're there, now where we're at is we've defined the syntax, and we've given it dynamic semantics for our language. And And so the only thing that remains is the type system. All right? And we have some goals in mind, okay, for what we want the type system to do. Okay, we're not doing this for no reason. All right? And one of the things that we really want to do with the type system is to rule out programs that will have bad runtime behavior, right? Like I said, if none of the rules apply, if none of the big step evaluation rules apply for a given program, it gets stuck at some point, right? And that's bad. That means there's an error. Okay, so we want to design a type system in such a way that whenever a program is well typed, according to our type system, then it's guaranteed to not get stuck when you run it. Okay? And so we'll have a more, well, this is called a type safety property. Okay? So, it's a property of the type system with respect to the semantics, that you say, okay, given this semantics and this type system, once we have it, then any program that's well typed will definitely evaluate to a value, without getting stuck. That's kind of what we want. Okay. So there's it really at its core, the type system is about sort of predicting runtime errors before they happen. Okay, and doing so without running the program. Okay, the idea is that it's static. Okay, that the type checking is a form of static analysis, where you're just looking at the program without actually running it. Just looking at looking at the syntax, really, kind of looking at the static structure of the program and trying to make predictions. Okay. How do I want to navigate this? Yeah. Well, so I guess we can draw that distinction here, because there is such a thing as dynamic type checking. Okay. So let me go ahead. Okay. Okay. So there is such a thing as dynamic type checking, which you're probably familiar with Python, for example, or Pirate if you don't use the static type checker. Okay. And so dynamic typing means that actually it's not a static analysis. It doesn't run before the program runs. It's not really predicting anything. It's just there to kind of prevent seg faults, essentially. So it means that types are checked at runtime. Okay. So, like for example, I don't know, like if you try to add two numbers together in Python. Okay, well, it doesn't actually know a priori that the operands are numbers, so it has to check at runtime. It has to say, well, first of all the values at runtime they aren't just their values, they have some additional data attached to them as well, like what type they are. So now, all your values have to carry what type they are. So then, the plus operator, whenever it tries to add two values together, it can pull out the type fields and make sure that they're compatible, and then pull out the actual value fields and perform the operation. Okay, and so at the very least, if you try to add a number and a Boolean or try to do something stupid, it's being careful. It's gonna catch that and throw an error in like in a principled way. Okay, it's not just going to cause a seg fault or anything, but it's still, there's obvious performance downsides for this. For one, okay, because objects have to carry type information, and there's just extra checks that happen at runtime, right? The dynamic checks. So there's pretty obvious performance downsides to doing dynamic type checking. Okay, and it also means that you don't actually get the error until it happens at runtime. Okay, so this isn't predicting anything for you. So it's really not that great, but sometimes it gives you a little more flexibility, right? That's why there do exist dynamically typed programming languages, because you can play kind of fast and loose, and some people like that.
This says objects what type info?
Carry. Sorry. Yeah, it just means your runtime objects have to actually carry with them what type they are. You know, they'll have like a tag that says, "Well, I'm an integer" or whatever. Okay. So then the other approach here is static type checking. Okay. So, you know, types are checked before. Okay, before runtime. You don't have to run the program to check the types. Okay, so there's actually performance benefit of this, of course, because now at runtime, all of your operations can just assume that things will be the right type, because the static type checker has already guaranteed that for you. Okay, so you know your runtime values don't have to carry any additional information, and there don't have to be any runtime checks for types at all. Okay, and so you know it might look kind of dangerous if you look at the code that's generated, but it's all going to work out because the static type checker has guaranteed it. And of course, that's if your language is type safe, right? That's if you've got that type safety guarantee that a well-typed program doesn't go wrong. But that's not always the case, and it's technically not the case in Pirate because they have that backdoor stuff you can do with the any type, you know. So that's one of the reasons why that stuff is not very good, because it violates type safety. So yeah, let's see. Yeah, so I suppose I don't have another bullet point there. Okay, so like suppose you've got something like this. Okay, x has type number. Okay, and say the type checker determines that that's true for some x. What does that mean, right? What does it mean? X has type number. Okay, like in Pirate. Well, you know, the way that you interpret that, assuming that there's no, you know, trickery going on with the any type or anything, but you know, assuming that we're sticking to the type safe fragment of Pirate. Okay, what does this mean? It means that you know, x evaluates to a number value. Okay. Okay, you know, or diverges. You know, it could loop forever. Okay, so when we say that x has type number, what we're saying is that, well, either x is some expression that loops forever, or it evaluates to a number. So if it produces a value, the value will be a number value. Okay. So right away we can see it's already kind of about predicting runtime behavior, right? That this is saying that x has type number is you're making a guarantee that whenever it does run, it'll produce a number. Okay. And so other parts of the program that use x can rely on this being true, and they can rely on it being enforced by the type checker. Okay. And so you know they don't have to do extra checks. When you write a function in Pirate that takes a number argument, you don't have to say, well, what if it's a bool and what if it's a string, right? You just get to assume that it's a number, and that's guaranteed and enforced by the type checker. Okay, so that means that you know no matter where you're at in the execution of a program, any argument passed here, if the parameter has type number, then it'll be a number value at runtime, no matter what, as long as you're not using the any type. So. Okay. Right, and you know, I'm assuming we're using the static type checker, of course, and so it is a form of static analysis. So there's this general idea of static analysis of programs. Okay, which is the idea of you know, just analyzing a program without running it. That maybe you want to check for some property. So for a type checker, it's just checking for a well-typedness. It's checking if the program is well-typed. So it can analyze the program without running it and tell you yes or no. It's either well typed or not. Okay, and there are other static analysis tools out there that can check for all sorts of things. They're like linters that can, complain about bad style and stuff, and they do that without running the program. They're just, inspecting its static structure. Okay, but there are some interesting limitations with static analysis. Okay, that there's only so much you can do without running the program. Okay, so one of these things is it comes down to the halting problem. Okay, so I don't know if you guys have learned about the halting problem yet. Yeah, so I think you really, I know like in computation theory you really dig into it. Okay, and so so here's an example of one kind of property that you might want to check with the static analysis tool, is whether or not the program always terminates on all inputs. Okay, suppose you wanted to write a tool that's kind of like a type checker, except it's a termination checker. It can take any program and tell you yes or no. This program, well, maybe it takes a program and the input to the program and tells you yes or no. Either it terminates on this input or not. Okay, and if you say the halting problem, then you know that sort of thing is not possible. Okay, it's impossible to have such a decider for the halting problem. Okay, you can't have a static analysis tool that perfectly decides the halting problem. Okay, and that turns out to be a more general limitation. Okay, and so there's something called Rice's theorem, which states that, go ahead and write it here, actually any, or I'll say all, non-trivial semantic properties of programs are undecidable. Whoops, there's a pretty strong result here. Okay, so what do we mean by non-trivial? Non-trivial just means that it's not the case that all programs satisfy the property, or that no programs at all satisfy the property. Because in that case, that's a trivial property if it's just trivially true for every program no matter what, because then, well, you already know the answer before you would ever run the checker on it. It's just, because it's always true or always false. Okay, so a non-trivial property is one that is like true for at least one program and false for at least one program. Okay, and semantic properties essentially mean that you treat the program like a black box where you can't look inside, and you're just reasoning about the input-output behavior, okay, or whether or not the program terminates or throws an error. Okay, so it turns out that actually all such properties like that are undecidable, and you can prove that by reduction to the halting problem, where you can just say, well, okay, suppose that you had a decider for some non-trivial semantic property, then you could actually use that to implement a decider for the halting problem. Okay, I can show you an example. Like suppose you had a decider for like a program P, the input program. Well, let's see. Like returns the value 1. Okay, that would be a semantic property of programs. Okay, so supposing that you had some kind of magical decider for this property. Okay, it's a very simple property. You might think that you could possibly do that. You could come up with some tool that like takes a C program and tells you whether or not it returns 1. It would work for any program. Well, if you had such a thing, then you could use this to implement a decider for the halting problem, where say, it takes a program and an input. And what would you do? Well, you could just ask D what happens on the following program that just kind of, runs P on X and then returns 1. Okay? And now, here you have a program that returns 1 if and only if P terminates on X. Okay? Okay, and so this would actually now be a decider for the halting problem. Okay, and we know that that's impossible. That you cannot have a decider for the halting problem, and so that means that the existence of this decider for this little property also is impossible. Okay. Right. So what this means is that we are fundamentally limited in what we can do with static analysis. That lots of interesting properties that you might want to check are not going to be checkable perfectly. You cannot perfectly decide a lot of these properties. So, the one that we're interested in, there's a semantic property that we are particularly interested in here with the type checker, which is just whether or not the program goes wrong, right? Whether or not it it gets stuck or throws an error, right? That's what we're interested in. And so we would really like for our type checker to be able to perfectly decide that property. The type checker should be able to look at your program and tell you yes or no, is this program going to throw an error or not, right? But we know because of Rice's theorem that that's not going to be possible, that we can't write a type checker that does that perfectly. And so we have to resort to something else. And we have to resort to what's called, conservative analysis. Okay? Whoops. Okay, which pretty much means playing it safe. That we're going to have to kind of approximate. Okay, so suppose I could draw a thing. We saw something like this already, where there's kind of a hierarchy here of sets of programs. Right. So at the outside we've got like all strings. All strings of like ASCII characters. Okay, so you've got the set of all possible strings, and there's some subset of that is like the set of syntactically valid I'll say scheme 0 programs. Okay, so among the set of all strings, there's some subset that are the syntactically valid programs for us. Okay, but then there's even further refinement. There's a smaller subset of programs that I'll call safe. Okay, these are the programs that don't throw any error. Okay, or maybe we'll say that under any environment they won't throw an error. Okay, something like that. So you'd say, P is safe if for all environments, then interp and P gives you a value, it doesn't throw an error. Okay, there's okay. Okay, right, there exists a value. Okay. So this is a little subset of the program. This is really what we want to capture. It would be really cool if we could write a program, a type checker program, that decides membership of this set. It can take a program and tell you perfectly whether it's in this set of safe programs or outside of it. Okay? But we aren't going to be able to do that because of Rice's theorem, like I said. So what we have to do is conservatively under-approximate the set of safe programs. Okay, so what we're really going to be able to decide membership of is an even smaller set. Okay? These are the well-typed programs, according to our type system. Okay, so what that means, and this is a proper inclusion. This is a proper subset relation. So there do exist programs in here that technically are safe, that won't throw an error, but will be rejected by our type checker because it can't tell. It's not that smart. Okay, and similarly, this is a proper inclusion as well, that there exist syntactically valid programs that are not safe. Okay, what was an example of that? Like, if 0, then anything. Okay, this is syntactically valid. Okay, it's a well-formed program according to our grammar, but when you run it, it sees that there's a number here instead of a Boolean and throws an error. Okay, so there's a syntactically well-formed program that's not safe, and then I can show you a safe program that won't be well typed. Okay, see an example of that. How about if true, then 1 else, I'll just say x, where x is an unbound variable. Okay, so if you look at this program, well, when you run it, since this is true, it will always take this branch and evaluate to 1, and it won't try to evaluate x. And so, this is technically a safe program. It's not going to throw an error. Nothing's going to go wrong when you run it. Okay, but our type checker will reject this because it's going to see that that x is unbound, and it'll reject. Okay, or maybe to be more clear, get rid of x and say something like, plus 2 false. Okay, here's another one that this is safe because it's never going to actually evaluate this side, but it's not going to be well typed because this expression right here is not going to be well typed because it's trying to add a number. Okay. Right. I'll show you another example. Let's see. How about this? Plus 1 if true, 2 false. Okay. So here's another program that is safe, technically. That you're going to add 1 to the result of this if expression, which, since this is true, will evaluate to 2. So you'll have 1 plus 2, and it'll all work out fine. Okay? But what we're going to have as a type checking rule, we'll see that this will not be well typed because the types of the 2 branches are not the same type. Okay? This is number, and this is Boolean. Okay? So the type checker in general, when it sees an if expression, right, like this is a particular case where it's kind of obvious. It's like, well, this obviously evaluates to true always, and so the whole expression will always evaluate to the left side. Okay, but in general, the type checker needs to be able to deal with every possible situation. So the general setup, like this. So this kind of reasoning kind of boils down to asking, like, does this expression evaluate to true always? Okay, or is it possible for it to evaluate to false? Always true. And what we're looking at here is a non-trivial semantic property of an expression in our language. And, well, I suppose you could do this for scheme 0 because it's the programs always terminate. Okay, so you could actually, our type checker actually could just run the expression, and it'll be guaranteed to terminate and produce the answer. Although I suppose it might not be able to do that either if we're considering all possible environments. So perhaps not. Then you'd have to try all of the different possible environments. Okay. But yeah, so in general, you can't do this. Okay. In the general case, you're not going to be able to determine whether the condition expression here is like always true or always false or anything like that. And so you have to use kind of more broad, kind of coarse-grained rules for the typing rules. So what are the typing rules going to be for the expression? Like, well, we'll just say this needs to have type bool, and then these need to have the same type, whatever it is. Okay, and that's something that we can do. Okay, but it's going to rule out some programs that really are safe. But the type checker is kind of not smart enough to see that. It doesn't even try, and it's just playing it safe. It's being conservative, and that's why the set of well-typed programs is going to be a strict subset of safe programs. Okay. Yeah. Right, and like we said, I mean, this essentially boils down to the halting problem, because, like, suppose that our language is Turing complete, then when you ask this question, is E1 always true? It's like, well, one thing that could happen is that it could loop forever, right? So if E1 looped forever, well then at least this wouldn't evaluate the false. So I guess you could, like, if you think of it that way, maybe you're really asking, is it possible for E1 to evaluate the false? And it's like in order to do that, you first have to be able to determine the halting problem. And E1 can be some arbitrarily complicated expression that it's not obvious if it terminates or not, and you really need to have a decider for the halting problem to figure out. So, yeah. So we're going to be doing, the type checker is an example of conservative static analysis. And so, don't have a whole lot of time left. So we might end it here, pick up next time. We could solve a quiz today. All right. Yeah. So what we'll see, like in this diagram, probably in the languages that you're used to, this is sort of like, these aren't really on equal footing. Right? The dynamic semantics is really like kind of the main part of this, and the static semantics is this little thing on top, off to the side. And okay, but it's possible to really expand and enrich the type system of the language so that it takes up, a much bigger share. It's sort of it's like equal status with the dynamic semantics. It's just as important, if not more important, in some languages. All right, so let's just see if we have a quiz. Okay. All right. See you Wednesday.